So in this video we're going to show an example of integration using the technique of u-substitution in an example involving trigonometric functions. We're going to have two slides. We're going to do two separate examples. So in the previous video we looked at an example involving polynomials, but the spirit of u-substitution is going to be the same as it was in that video, in the sense that what we're looking for is an expression that we're integrating, for which if we make a u-substitution for a specific piece of it, so in this case, for example, if I did u equals the tangent of x plus 2, when we take the derivative of both sides with respect to x of that u-substitution, so let's do that, du dx, take d dx of both sides, and then the derivative of the right-hand side is just going to be the secant squared of x. When we take the derivative of the u-substitution, we want to see the derivative of something in the expression we're integrating showing up. And in this case, the secant squared of x shows up right here. So the derivative of the u-substitution varies from what we see here by only a constant, and that's the key. That means that a u-substitution is probably going to work in this particular case. So here, if I rewrite the integral, so 2 times the secant squared of x times the tangent of x plus 2 dx, and then we recognize this is an integration, so the constant can be factored out of the integral, so we get twice secant squared of x times the tangent of x plus 2 dx, and then if I multiply both sides of this by dx, I'm going to get du is the same as the secant squared of x dx. So now I'm in a position to make u-substitution. So I'm going to get 2 times the integral, and the tangent of x plus 2, we're going to substitute that substitute u for that expression. So replace the tangent of x plus 2 with u, and then the secant squared of x dx, the secant squared of x dx is the same as du. And now we have an integral in variable u, and this integral is just a power function u to the first power, which makes it easy to integrate. We're going to get 2 times, we increase the exponent by 1 and multiply by the reciprocal of the exponent, and then we add to that the constant of integration. 2 times a half is 1, so we get 1 u squared plus a constant, and then we want to convert back into variable x, so we know u is the same as the tangent of x plus 2, so we can replace u here with the tangent of x plus 2. 19 times out of 20, when you make a u-substitution, what you want to recognize is you could have done the integration without making the u-substitution. It's just an application of the chain rule, but making a u-substitution can sometimes make things a little bit cognitively easier to think about. So next example, still a trigonometric example. So we have cosine squared of x times sine x. So I've got a function composition sitting right here. I have the cosine function inside of the squaring function. And what I want to notice is that if I do the substitution u equals the cosine of x, then du dx is just equal to negative sine of x, which varies, and so the derivative of the cosine varies only by a constant negative 1 from the sine of x that's sitting there being multiplied to the function composition here. So u-substitution is going to be a tool that I can use. So again, like we did in the polynomial video, we want to recognize there's 2 ways to deal with this. Well, there's at least 2 ways to deal with this. Cosine squared of x, sine squared of x dx, or integral of cosine squared of x sine x dx. So one way is to multiply both sides by that dx. You're going to get du equals negative sine x dx. And then if we look here, we don't have the negative sign, so we want to recognize if we put a negative sign in there, then we would have a negative sine of x dx. But we can't just arbitrarily insert a negative sign, so I would need a double negation. I would need to put a negative sign on the outside as well. So the opposite of negative is a positive. And then if I do that, I'm ready to make my u substitution. I go the opposite of the integral, and cosine gets replaced with u. So we get, instead of cosine squared, we get u squared. And then negative sine x dx, negative sine x dx is the same as du. So we make that replacement. Now I have a power function. I'm going to integrate it. So it's going to be the opposite of u cubed, and I need to multiply by the reciprocal of the exponent I increased by 1. And then it's plus a constant of integration. And then we need to convert back to the x-coordinate world. So we're going to replace u cubed plus c. We replace the u and the u cubed with the cosine of x, because that is what u represents. And it would be fairly customary to write this as the cosine cubed of x plus c. Would be kind of a standard notation. So the other way we could have dealt with this right here, when we got to this spot, is I could have done two things at once. I could have multiplied both sides by the dx, but also multiplied both sides by a negative to get negative du equals sine x dx. And then I could have made my substitutions. I could have said I'm going to integrate cosine of x squared, but cosine of x is u. So I get u squared, and then replace sine x dx with negative du. And you'll notice that we wind up with the same integral either way. So when we integrate this, we're going to get the same result as we did before. We're going to get the negative 1/3 times the u cubed plus a constant of integration. It's just going to be negative 1/3 times the cosine cubed of x, replacing the u with the cosine function, plus the constant of integration.